This is Mrs. O'Neill for AP Chemistry, Chapter 7, Section 8, Trends for Selected Nonmetals. So hopefully you'll understand the periodic trends between hydrogen and groups 16, 17, and 18. Again, I suggest to pause, fill in the blanks, and then play to hear my words. So these are all basic properties of hydrogen, and it's really its own group. It's the only one that has that one valence electron. It forms that +1 charge. It's a diatomic. It's up in that upper left-hand corner of the periodic table on the metal side, even though it's a nonmetal because it's a gas, but it has a positive charge instead of a negative charge like most of your nonmetals. So it's in a group all of its own. And just to remind you that it can form what's called a hydride ion. You don't see it often, but it can happen. So group 16 is really the oxygen group. So we talk about oxygen as O2, the stuff we breathe, and ozone, O3. And of course, they're both gases, but they're called allotropes of each other because they have different forms of the same element and in the same state. So that's what's pretty neat about these allotropes. Another kind of allotrope that you might be familiar with is carbon, your graphite that you use in your pencil, and the carbon diamond that people like to buy their spouse or their partner if they're going to get married. So you have oxygen, O2 and O3. And then you also have something like carbon and graphite versus diamond, and those are allotropes of each other. Group 17 are called the halogen groups. They exist as those diatomic molecules. They form that -1. And you want to remember that HF is a weak acid, where the rest are strong. And how do we know that it is a weak acid versus strong? Hopefully in your brain you're saying, yes, it is not on the list, right? It's on the list or not on the list. So HF is not on the list. It is weak. The noble gases, you should know this information already, that they're unreactive. They have that filled S and P subshells, so they have that octet rule. They're not going to react with anybody. So in closing, you should have watched the following video on periodicity. So hopefully this was a good review for you. Here are my notes. So again, periodicity is patterns that we see on the periodic table, and they're determined by the electron configuration. That's one of the reasons why they put the periodicity chapter after the electron configuration, so that you can kind of put them together, understand how they're related to each other. And of course, in electron configuration, we're building from lower to higher energy levels. So what are the trends? Besides the fact that you need to know them, which way does it increase or decrease, you should really understand why, for instance, ionization energy is increasing as it going to left to right on the periodic table. Why is atomic radius increasing as it's going down the group? So hopefully with this information that he gave you and relating it to that Coulomb's law again about the atom, you'll be able to understand the trends so you don't really have to memorize them. So he gave you a nice little flow chart. Hopefully you went through that and understood it. And so what does that electron configuration help us do? To make predictions. So he also talked about how this F block and how it really truly looks on the periodic table. And the only reason why they take it out and put it underneath is so that all of the information can fit nicely on an 8.5 by 11 piece of paper. Now, if more and more elements get discovered or made, I should say, then I don't know where they're going to put them. Is it going to be another F block? Is it going to be underneath the F block, or is it going to be now part of the S, D, and P block? Not sure. So he talked again about Coulomb's law, and Coulomb's law guides us to that electron configuration. Again, because he talked about the protons in the nucleus, he talked about the electrons, he talked about shielding, and he talked about this equation. So he talked about how Coulomb's law, you talk about those protons that have a positive charge in the nucleus and the electrons that have a negative charge on the outside. So you multiply those charges. Again, going back to this equation, you're going to multiply those two charges. Well, if you multiply, obviously the bigger those charges, the more and more positives and negatives that are in an atom, the bigger that force of attraction it's going to be, the bigger the force. So, but if we go back here, we're really dividing by the R, which is the radius. So if we divide by the radius, that means the further those charges get from each other. So again, back here, so from this electron to this proton, and the further and further and further away that they get, the smaller that force is going to be, the smaller that force of attraction is going to be. So again, that shielding is the electrons on the outside are shielded from those on the inside. And we'll talk a little bit more in detail about that later. So again, he went through the trends. Hopefully by now you know what ionization energy is and what the trend is. You know the atomic and ionic radius, the trend and the why. Electronegativity, again, how bad an atom wants an electron. You should know that trend. And the typical ionic charge, which by now you should know, at least the ones that he went over, +1, +2, +3, -3, -2, -1. And he didn't really talk about those noble gases, but those noble gases do not have a charge, and that's why the atoms want to work closely with them, or closely to get to them. He talked about Mendeleev and his first periodic table, and he's the father of the periodic table because he's the one who made those amazing predictions about how these, it's hard to see here, but those question marks there, here's an example. Those question marks, really, he said, oh, you know what, one day an element is going to be discovered, and boop, it goes right in there. And he was correct. That's what was amazing. It's one thing to make the predictions and, oh, yeah, it didn't happen. Oh, well. It's another thing to make those predictions and it comes true. And then he talked about this Julius von Meyer. He also worked on the periodic table at the same time, but he's not as well known because he didn't make those predictions. He just kind of started grouping elements together. And then he talked about material design, and one of the main reasons why trends in the periodic table and the location of those elements is so important is because we can take those elements, like he took silicon dioxide and he said what we can make out of it, and then he said, oh, well, if silicon dioxide can do something, how about like a tin dioxide? Because they're in the same group, what would tin dioxide do? And of course he said that it would be very similar, but it still would be a new material. And again, he went back to the flow chart. All right, see you in class.